motion. We are very familiar about the word motion. We all are seeing several moving bodies like motion of people, vehicles, trains, aeroplanes, birds, and so on. We also know that due to the motion of Earth, that phenomenon like sunrise, sunset, changes in seasons, etc. occurs. How can we say whether the bodies are at rest or in motion? If Earth is in motion, why do not you directly know the motion of Earth? Did you ever feel that when you are sitting in the rest position of a train, it appears to move when it is rest? To know the answer for this question, we need to understand the term relative. To understand the motion of any body, we need to understand the meaning of the word relative, which plays an important role in explaining various ways of motion. What is relative? We use many statements in our daily life to express our views. The meaning of a statement depends on the relation between the words used in it. Does the every statement have a meaning? Evidentially, the answer is no. Even if you choose perfectly sensible words and put them together according to all the rules of grammar. A statement has a meaning only when there is a relation between words. Similarly, there may exist other situations in our daily life where we use statements having meaning depending upon the situation. Let us observe the following example. If we take the height of you and your friend as A and B, the height of A is 4 feet and the height of B is 5 feet and the height of C is 3 feet. Now, is man A shorter? Is man B shorter? Or is man C shorter? To know the answers for these questions, just compare the heights of these persons. When compare A and B, A is shorter than B. When compare A and C, A is longer than C. For the same person, depending on the comparison, sometimes A is shorter and sometimes A is longer. Here, the height of the person, that is, the man in shorter or longer, can be explained. When the height is related to another person's height. Or, we can say that height is relative. Take two balls of masses A, B are 2 kgs, 4 kgs. What about the weight of the ball A when compared to B? Weight of ball A is smaller. When we compare it to another ball C of mass 1 kg with the ball of mass 2 kg, now the ball A is larger than C and smaller than B. So, we can say that size is relative. Two persons A and B are moving opposite to each other on a road. On which side of the road is the house? Is it on the right side or in the left side of the road? Position of the house depends on the person. For person A, the house is on right and the person B, the house is on the left side. That means the position of the house depends on the observer, that is, relative to the observer. We can clearly mention the person depends on the person relative to the person. We are saying the particular position of house. Up and down. By observing these examples, we say that everything on the earth is relative. Like the terms right and left, up and down, short and long, small and big, motion is also relative to the observer. To know how the motion is relative clearly, let us observe the examples. Are you going in bus? We are moving in bus. We observe the surroundings like trees beside the road. We feel that we are moving in particular direction. The trees moving also with you in opposite direction. But the person who is not moving in ground, observe that there is no change in the position of a tree. For the same tree depends upon the observer. The tree may be at rest or in motion. In this way, the motion of a tree can be explained relative to the observer. Now, we are able to answer the questions. What is relative? What is the state of tree for ground observer? What is the state of the tree for a moving person in bus? If person moves towards east, then the direction moving tree is. Now we are able to define the motion of an object. If we take a duster that is placed on a bench, until and unless we are applying any force on a duster, see tomorrow the place of the duster does not change. It stays in the same position. That means if the time, that is, days going on, both the position of duster does not change, then we say duster is in the state of rest. Rest. Rest is defined as the position of a body does not change with respect to time and surroundings. Then what about the motion? A body is said to be in motion when the position of a body continuously changing with time, relative to an observer. Motion. The position of a body continuously changes with time, then the body is in motion. Now, we all know about some of the physical quantities changes whenever the body is in motion. For example, the body moves from one place to another place, then the total path traveled by the body is called as distance. Distance. The path traveled by the body is called as the distance. Now, the ant goes from point A to B. Then, the total path length gives us distance. For example, the length is 4 meters. That represents magnitude. From what to what we have to take 4-meter length can we do? So, we do not know the direction, 80 distance having only magnitude but not the direction. It is called a scalar quantity. In the above diagram, A is an initial point and B is the final point. Here, the length of the path between A and B is 2 meters, then that is called a displacement. Displacement. The shortest distance between initial and final positions, that is 2 meters magnitude and direction from initial to final position, is called as displacement. Displacement is a vector quantity. The physical quantity having only magnitude is called a scalar quantity. The physical quantity having both magnitude and direction is called a vector quantity. A vector is geometrically represented as A, B, where the length of the line represents the magnitude and arrow represents the direction. Point A is called tail and B is called a head. The length of the body can be measured in meter or in centimeter, etc. Here, distance and displacements are also measured in centimeters or meter. SI unit of displacement is meter. CGS unit of displacement is centimeter. Magnitude. The number along with the unit is called the magnitude. Take a ball and throw it into the air some angle to the horizontal. Observe the path and draw it on a paper. Now we are able to know the distance and displacement. The straight line from A to B represents the displacement and direction is from A to B. The curved path length gives us the distance. Here, observe the distance and displacement. The magnitude of the displacement is less than distance. But distance and displacement are equal when body is moving in a straight line path. On a busy road, it may not be possible to move in a straight way. So, a car moves along different ways. The points A and B are called the initial and final points. Draw the displacement vectors for two situations. By observing these two diagrams, we are saying that distance is greater than displacement. The displacement and distance are changing with respect to time. So, these quantities are called time-dependent quantities. Now, a body is moving in a circular path. After covering one revolution, then initial and final points are equal. Then there is no difference between distance and displacement. So, displacement is 0. Average speed and average velocity. A train going from Visakhapatnam to Hyderabad on a way going it reaches to Vijayawada and finally reaches to Hyderabad. Then the total distance between Hyderabad then is 720 kilometers and the time taken by the train to cover this distance is 12 hours. Then the distance covered by the train in each hour is total distance divided by total time is equal to 720 divided by 12, which is equal to 60 kilometers per hour. But we are not saying that exactly in each hour the distance covered is 60 kilometers. Obviously, the answer is no. Because sometime train moving fastly, if any stations present in this way, then fastness is decreased. So, there may be some variation in distance covered by the train for each hour. So, we have to take average of distance covered by the train for each hour. It is given by a new physical quantity, that is average speed. Average speed is equal to total distance divided by total time taken. Let the displacement of the trip in above example is 360 kilometers the northwest, then the displacement in each hour is equal to 360 kilometers divided by 12 hours northwest, which is equal to 30 kilometers per hour northwest. Then the displacement of an object per unit time is called average velocity. Average velocity is equal to displacement divided by time taken. The quantity average speed explains the average motion of a body in a given time interval. Average velocity also explains the motion of a body in a given time interval. With the help of average speed and velocity, explain the motion of a body in a given time. But we do not know about the motion of the body at a particular instance of time. So, the motion of a body at particular instance can be explained with the help of other physical quantities, speed and velocity. Speed. While conducting a running race, if the distance is fixed among all the runners, who reached the destination first was declared as a winner. He take less time to cover that fixed distance than others. Now, we are not fixing the distance. In this case, who runs more distance in the particular time was declared as the winner. By the above observations, we can say that a person takes less time, moves faster than others. Takes less time means moving fastly with more speed, so speed into 1 divided by time. Distance moved by the person in a given time is more. That means a person is moving fastly. So, speed into distance. Speed equals to distance divided by time. It can be defined as the distance travelled by the body in unit time is called speed. But the speed of the body changes continuously with time. Its speed at any instance is known as the instantaneous speed. Instantaneous speed. It is calculated by finding the distance travelled by the body in a very short time interval and then dividing the distance by the time interval. Note: the speedometer of the vehicle measures the instantaneous speed. Consider a car moving along a straight road with varying speed. Then the motion of that car describing the motion of a body along a straight line is distance-time graph. Now we have to find the speed of the car at the instant of time t3 for distance given motion, and the average speed during the time interval for t1, t2, which includes the instance t3, that is the average speed, which is equal to s2 minus s1 divided by t2 minus t1. Thus, we are calculating average speed for an average short time interval in addition to time. At that instance, the value of average speed would not change because that time interval is so short interval. The instantaneous speed is represented by the slope of the curve at that instant of time. The slope of the curve at any point can be known by drawing the tangent to that point. It gives us the speed at that instant. If the slope is large, the speed is high. The speed is low means slope is small. Simply, speed gives us how fast, how slow body moves. In addition to this fastness or slowness, in which direction the body is moving with that much of speed, can be explained with another physical quantity, that is velocity. Because with the help of speed, throughout the journey, we do not know the direction of the going bodies. We need to define a new physical quantity, that is velocity. Velocity is the speed of an object. It also tells us about the direction of the motion of body. It is represented by directed line segment like the geometrical representation of vector. Because it is also a vector quantity, it has both magnitude and direction. The length gives speed and arrow gives the direction of the motion. If a body moves in a curved path, now we have to know the direction of velocity at particular. The tangent drawn to that point gives the direction of velocity at that point. Does the direction of the velocity is constant? To know the answer for this question, do this activity. A stone is tied to a rope, and wire the rope with your hand. And carefully observing the motion of a stone for every instant, and also observe the direction of motion of stone, you will notice that the object on a straight line along the tangent to a circle at a point where you start gives the direction of velocity is tangent to the path at the point of interest. The SI unit of velocity is meter. In our daily life, we are observing so many types of motions where, in some cases, velocity of an object which is in motion is constant, but in other cases it is continuously changed. Which motion is called uniform? Uniform motion. Consider a cyclist moving on a road. The distance covered by him with respect to time is given in the following table. We draw a graph for distance and time. We draw a graph. Graph is a straight line. It indicates that cyclist covers equal distance in equal intervals of time. From the graph, you can understand that the instantaneous speed is equal to average speed. For every time interval, the distance covered by the body is constant. Then we can assume that velocity is constant. Non-uniform motion. In our daily life, in many situations, we are observing such type of a motion. If we take a moving train, it starts from rest and leaving to any station, it starts slowly after speed is gradually increases. After moving certain distance, speed is gradually decreased and stops for some time in any station. That is one of the example of non-uniform motion. Consider a moving cycle on a road. The time is going on the distance moving by him is given in the following table. Draw a distance versus time graph for the given table. What is the shape of the graph? Is it straight or not? If it not, then what is the shape of the graph? Observing the motion of a ball on an inclined plane. Take a ball and release it from rest. From the top of the inclined plane, the position of the ball at various times as shown. What is the path of the ball on the inclined plane? How does the velocity of the ball changes? We observe that the ball moves down on the inclined plane, its speed increases gradually. What about the direction of motion of the ball? The direction of the motion of the ball does not changes. It remains constant. Now set up the inclined plane as shown. Now move the ball in upward direction. Now observe the speed of the ball and the path of the ball. By observing the above two, we say that speed changes, but the direction of motion does change continuously. Observing uniform circular motion. Roll a stone which is tied to the end of the string continuously. Draw its path and observe the motion and velocity at different positions. We observe that the time taken by the stone to complete the rotation is same always. So, we can say that the speed of the ball does not changes continuously. Then, coming to the direction of the moving, that is nothing but the path of the stone. It is changes continuously. That means the direction of a body changes continuously. Can you give few examples for motion of an object where its speeds remain constant but velocity changes? Yes. We know Earth revolves around the Sun. In this case, speed of Earth remains same. How can we say? Means to complete one revolution, time taken by the Earth is same. It indicates that speed is constant but direction changes continuously. Observing the motion of the object thrown into air. Thrown a stone into the air by making some angle with the horizontal. Observe the path taken by it. Draw a diagram to show its path and velocity vectors. Is the speed of the stone is uniform? No. Speed of the stone while it is going up, the speed is continuously decreases because gravitational force opposing the motion. And at the maximum height, the velocity of the vertical component is 0. and moving down, its velocity increases. Here, both magnitude and direction of velocity changes continuously throughout the motion. Can you give some more examples where speed and direction simultaneously change? For the above activities, you can conclude that the change in velocity takes place in three ways. Speed change with constant direction. Speed is constant with changing the direction of motion. Speed and direction both are changing simultaneously. Acceleration. Here, we know that velocity gives us the speed of the body and the direction of the motion, a moving body. How the velocity changes? Either changing the speed or the direction of motion, we can change velocity. At what rate the changes in velocity takes place can be explained with either a new physical quantity, that is acceleration. It gives an idea how quickly velocity of a body is changing. Now, we have a doubt. What is acceleration? How can we find the acceleration of a body? In order to know the answer for this question, let us observe these examples carefully. If we are traveling in a bus or a car, when the driver presses the accelerator, then we are experiencing of that acceleration. Our bodies press against the seats due to the acceleration. Suppose we are driving a car. Let us steadily increase the velocity from 30 km per hour to 40 km per hour. In 1 second, and 40 km per hour to 50 km per hour in the next second, and soon. In the above case, the velocity of the car increasing 10 km per hour per second. That is nothing but the rate of the change of velocity of an object is called acceleration. We are having two types of accelerations: uniform acceleration and non-uniform acceleration. Uniform acceleration. If the velocity of a body continuously increases, that is called a uniform acceleration. That means for every 1 second the change in velocity is 5 meters, then we can say that body is moving with uniform acceleration. Example: generally, we are observing the free fall of raindrops is an example of uniform acceleration. Non-uniform acceleration. When a body is moving, then the velocity of the body increases like this: in 1 second 5 meters, and the next second 7 meters, and the next second 15 meters. Here there is increase in velocity, but it is not increasing uniformly. We can say that body is moving with non-uniform acceleration. Motion of the passenger train is the best example of non-uniform acceleration. Motion of a body in a curved path also an example of non-uniform acceleration. Note: what about the acceleration of the body when the velocity of a body remains same? That means velocity does not increases or decreases. In such a case, there is no change in the velocity, so acceleration of a body in such case is zero. Acceleration is also a vector quantity because it has both magnitude and direction. The direction of velocity represents the direction of acceleration. It is defined as change in velocity by time taken. Units of acceleration is meter per second. By observing the diagram, the length of the vector at particular point corresponds to magnitude of vector at that point. An arrow indicates the direction of motion at every instant. Now, at which point acceleration is maximum, at which point the change in velocity is maximum, at that point acceleration is maximum. Does the motion process acceleration? Yes, because at every point there is a change in velocity. Note: if the velocity decreases at uniform rate, we say that the acceleration of the body is decreases. Then we say that is called deceleration or retardation, and it is also called as negative acceleration. We observe this negative acceleration when the body is moving upwards, or a ball thrown upwards, the velocity of the body continuously decreases. That means acceleration decreases. Then we can say that body is retarded. Note: if the speed of an object increases, the direction of velocity and acceleration are one and the same. If the speed of the object decreases, the direction of velocity and acceleration are in opposite directions. In such case, at a certain instant, speed becomes zero. If there exists an acceleration of a body at a point where its speed becomes zero for an instant, then the body returns in the direction of acceleration and moves continuously. If we want to find some of the physical quantities changes for the uniform accelerated motion, those are like displacement, velocity, average velocity, speed, etc. We are using equations of motion.